Greetings! This video will show you how to use geohashing in order to extract the exact location of where these wildly drawn smoke plumes are on the map. As a quick background, the NOAA hazard mapping system shows you the fire and smoke locations across North America, and these smoke plumes are hand-drawn by image analysts as they analyze smoke and fire from satellite images. So this is the website where we get data from, and this is a map of BC. If we take one of the polygon shapefiles that contain the smoke plume information, this is how it would look like on top of the BC raster. And so the goal here is to extract exactly the location of these smoke plume cells in BC. So you would essentially get a unique identifier for each cell, whatever resolution that you set. You can get the exact location with a geohash, and then you can assign a value with it however you'd like. And so because our goal is to use this information as part of a bigger project, which is to use a number of data sources as a input for a convolutional neural network, and then using these different data sets, we can try to predict smoke location and magnitude using CNN. So how do we do this? We found that from a time series analysis of all the smoke plumes in 2018, between the hours of 9 until about 7 p.m., there are rarely any smoke plumes drawn. And at first we speculated that perhaps the smoke plume analyst just simply did not work 24/7. However, after corresponding with the NOAA staff, we realized that the smoke plumes are not drawn during these times primarily because of low visibility of smoke plumes. So the analysts try their best to distinguish between fires and other heat sources and smoke and other sources of smoke, because highly reflective surfaces like mines or gas flares or solar panels can be mistaken as fires. So false positives are included in these data that we obtained from the NOAA. Because false positives are included, we feel that between the hours when smoke plumes are rarely drawn, the error of these data is too high, so we decided to not include data from between 9 and 7 UTC. And to take into account the differences in coordinate reference systems between this BC raster and the polygon shapefile, we decided that across datasets we will use WGS84 coordinate reference system. And even though the BC raster has WGS84 coordinate system, the polygon shapefiles actually are using the NAD83 coordinate system. Even though they're different, transforming between these two typically is not recommended because standard transformations can introduce errors that are large relative to their difference. So we can end up getting something that is even less accurate. And so we didn't want to complicate this project, so we didn't transform between the shapefiles and the BC raster because NAD84 and NAD83 and WGS84 are close enough, and transforming can actually introduce larger errors than not transforming. So we will try to introduce geohashing using Python. So essentially, geohashing is, so the goal is to extract binary features that indicate whether a cell in a grid of BC has smoke or not. And using geohashing, we're going to do this by assigning basically a location with a unique identifier. So we'll imagine that the world is divided into a grid with with cells. So in this map, you can see that, for example, Canada has the character C, because, I mean, you could be maybe in parts of the US and you could still have a location that starts with the letter C. So essentially every place on Earth is identified first with one letter or one character, or an integer, doesn't matter. So the first character in a geohash identifies the initial location as one of these cells, and this cell will contain another number of cells, so another 32 cells, and then each of these will contain another 32 cells, and so on repeatedly. Adding characters to the geohash subdivides the cell, and so we're essentially zooming in into more detailed areas, as you can see in this cell here, that you're zooming in more and more, and the more you zoom in, the longer your geohash will be. And the precision factor determines the size of the cell. For example, a precision factor of 1 creates a cell about 5,000 kilometers high and 5,000 kilometers wide, and a precision factor of 6 creates a cell that is about 0.6 kilometers high and 1.2 kilometers wide. So the cells are not always square is the key takeaway. And in our case, the geohashing method is used to turn each cell in the BC grid into a unique geohash that can be compared with the smoke plume polygon to indicate whether the cell has smoke or not. And so the Geohashparser class will take in the source polygon shapefile directory, the name of the individual shapefiles, because as you know, shapefiles cannot be read without its without the dbf and shx files that provide information on geometry, so they always have to be downloaded together. Anyway, that's why we need to have not only the shapefile itself, but its directory. And we write the results into a results file path, so we have to give it a file path. And one last thing we include as a parameter is the hours of the day to exclude, which we determine to be between 10 to 6 in this example. And the output would be a matrix of BC, a grid of BC with cells assigned 1 for smoke, 0 for no smoke, and -1 or null during the hours in which the smoke plumes are not usually drawn, or if they're drawn, the error is too big, so we are not including them. So we don't want to confuse the model, so that's why we're including nulls. And the bounding box of BC and the geohash precision are set as static variables so that we're not going to change them. So you can see there. Essentially, what this class does is we check the polygon shapefiles to identify if the shapes in the shapefile are within the bounding box coordinates of BC. And then we compute geohash tiles from polygons that are within the box. And so this is what all of this does. And I tried to name the functions exactly as what they do. So the first static method is just getting all the geohash in the bounding box and check to see if the geohashes are in this box. And then you start to compute the polygon shapefiles to see if they fall within the BC bounding box. And then this function is just for visualization, just to make sure that it's for debugging purposes, so you don't always have to do that one. And then writing the results array to file eventually. And yeah, so this is basically how geohashing works with polygon shapefiles obtained from NOAA HMS database.